So good afternoon, everyone. My name is Martijn Roosen, and I'm a PhD student at the Laboratory for Circular Process Engineering at Ghent University. And my PhD topic is on the deodorization of post-consumer plastic waste, on which I will give a short presentation today. So what we actually try to do at our research group is to go from open loop recycling, which is mostly the case, to closed loop recycling. And as Ruben before already mentioned, it's quite complex and not so easy and challenging to achieve that because plastic waste is very complex. It is very heterogeneous in terms of polymeric composition. And moreover, there are quite a lot of different substances that are present on the waste that complicates closed loop recycling. You have, for instance, inks that are present. You have labels that are present. You have organic residue that remains in the packaging, or there are certain additives that are added to the packaging material, and the substance that is in the main focus of my research is the odor. So plastic waste typically has a strong smell, and of course you don't want your recycled product to have a smell. So it's quite a challenge in the recycling industry to remove the odor from plastic waste. And of course, if you want to do research to deodorization, you need a method to quantify the removal efficiencies. And this was actually the first stage of the research that we have performed. So we have compared different techniques that are able to quantify deodorization via GCMS analysis. So the first method was SPME, so solid phase micro extraction. So we started with this method, and what we actually saw is that it's quite useful to identify VOCs, or volatile organic components, on plastic waste. But if we repeated this technique on a certain sample for 3 or 4 times, we saw that we got quite a lot of variation on the results. So actually this method is not repeatable, or not able to achieve repeatable results for a complex and heterogeneous waste stream as post-consumer plastic waste. So then we looked a little bit into other techniques, and then we came out on 2 techniques that are based on desorption of odor components. So first of all, we applied a technique on which we adsorb the odor components on an activated charcoal tube and then desorb the odor components from the activated charcoal to a solvent, and then we inject the solvent. And the second technique is similar, but we use a different adsorbent, and instead of a solvent we use an increase of temperature of the GCMS to gradually desorb the components. And what we saw is that both methods have much better results in terms of repeatability. So we got a relative standard deviation that was lower than 15%, which was what we were aiming for. And next to that, we also saw that both methods are quite complementary, as for instance, the activated charcoal can analyze components with a boiling point between 80 and 320 degrees, while the thermal desorption technique is more suitable for the more volatile components and can go for components with a boiling point until 30 degrees Celsius. So this was interesting to see, and we got a lot of knowledge on this analyzing techniques, and this was really necessary to go to the next step, which was really the deodorization experiments. So we have performed first of all a kinetic study on the deodorization of plastic films. So here we have investigated different washing treatments for plastics. So we have tested 5 different treatments, which was water, caustic soda, which is sodium hydroxide, a combination of caustic soda and a detergent, only a detergent and a solvent. And the solvents are coming up a little bit more in the recycling industry because of the challenge to gain high value recyclates. And we have performed these 5 different washing treatments at 3 different temperatures, namely 25 degrees Celsius, 45 degrees Celsius, and 65 degrees Celsius. And on the schematic visualization at the bottom of the slide, you can see a bit how we approached this in the lab. So maybe important to show is that we have performed the washing on shaking plate, as we call it, and with this shaking plate we can control the friction that is created and also the temperature of the washing medium, which are 2 important factors in deodorization. Then as a next step, we have separated the plastics from the solvent, and we have analyzed the odor on the plastic that remains. So we gained a lot of experimental results, and as a next step, we have linked a kinetic model to those results. So we have simulated various models that are available in literature, and what we saw is that a reversible first order model showed the best fit to our results. And this is quite important because, as you can see in this term, there is a word reversible, which actually means that not only desorption takes place, which is actually the deodorization process, but also adsorption can take place. And adsorption is, of course, unwanted because that actually means that odor components can migrate from your washing medium to your plastics, which is, of course, not what you want. Then when we look at the efficiencies that we have obtained with the different washing media, we see that caustic soda is not so efficient. And that was actually a bit surprising for us because caustic soda is often used in the recycling industry in washing processes. So we expected actually that this would result in a good removal efficiency, but it actually resulted in the lowest removal efficiency. And what we saw is that you actually need to add a detergent, or you can apply an organic solvent like we did with ethyl acetate. And then the removal efficiencies can really increase up to 80 or even 90%, depending on the conditions that are applied. So that was quite good removal efficiency that we obtained. Then as a next step, we have performed Aspen simulation. So Aspen is a chemical software or chemical simulation software. And we have investigated a few parameters that are relevant for the industry because that's actually our main objective. So what we have investigated is a solid-liquid ratio, the residence time of the plastics in the washing medium, and the recirculation rate of the washing medium. So actually how much of your washing medium is reused in the process, in the washing process. And what we saw is that the solid-liquid ratio is quite important, which is logical, of course. And if the solid-liquid ratio increases, then the removal efficiency will decrease, which is a logical result. So the better and the higher the solid-liquid ratio, so the higher the liquid ratio, the lower the removal efficiency. Then when we look at the residence time, we see that there was an equilibrium that is achieved after around 1 to 2 minutes. And that's actually quite good because in an industrial washing plant, the residence time in the washing medium is a bit higher than that. So in that perspective, it is a good result. But then the third factor that we investigated was the recycling rate of the washing medium. And what we saw there is that this is a very important factor. And if this increases too much, so if you recirculate too much of your washing medium, then there is a significant drop in the deodorization efficiency. And that we can actually link back to the model, the reversible kinetic model that we found out that was the best fit. Because what happens if you have too high recirculation rate, then the washing medium is actually gets saturated with your odorous components, and there is no way anymore to deodorize the plastics because the equilibrium is already achieved in your washing medium. So what we saw is that 60% is quite a critical value here, and in the industry, in the recycling industry, they often apply recirculation rates more than 90%. So that's actually one of the reasons, or one of the main reasons, according to us, why plastic waste is still smelling after they washed it in a recycling plant. So that's quite important conclusion of our study. Next to that, we were also a bit triggered by the fact that sodium hydroxide actually didn't work for PE films. So we were thinking, okay, maybe we should just make the exercise and wash all types of plastic packaging, all commodity plastic waste, with all types of washing media that we think could work on industrial scale. So it was quite a lot of experiments, but we really wanted to have a clear overview of what is working for which type of packaging. And in that perspective, we have identified the odorous components on all these types of packaging products, and we came out with a list of 170 odor components, which we have classified according to chemical group, and we have also looked up a little bit physical chemical properties. And there we saw an interesting thing, that namely if we plotted the log P value, which is the octanol water partition coefficient, which is a measure for the polarity of the odor component in terms of their packaging type, we saw that there was a little bit difference in the distribution of the components. So for instance, for PET bottles, you see that the distribution in terms of the log P value is a bit more narrow than, for instance, for PE films. And that is important to realize that not only the packaging type and the polymer that is used in that packaging type can vary, but also the physical chemical properties of the odor components play an important role in the deodorization process. Then my last slide, but with quite a lot of data, I would say here. So here you can see all the different washing media applied on the different packaging types for 25 degrees Celsius and 65 degrees Celsius. I will not go over too much detail, but what is important, I think, to stress out and to notice is that for PET bottles, you see that with caustic soda, there is quite a high removal efficiency, for instance, with 25 degrees up to 74.4%. While if you compare this with the polyolefin packaging types, you see that this is much lower. If you only apply caustic soda, so sodium hydroxide, for PE bottles, only a removal efficiency of around 36% is achieved. While if you add the detergent to those polyolefin packaging types, you see that the removal efficiency can increase a lot, up to 60%, 65%. And if you apply an organic solvent, this can even further increase up to 75% for PE bottles at 25 degrees, or at 65 degrees, even to 85%. So what you should really remember here is that caustic soda is not the main driver for deodorization for polyolefin packaging types. And what the recycling industry tends to do now is to mimic the process that they use in the PET bottles, because that is already more mature. But in terms of deodorization, that is most probably not the most suitable solution, and they should really think to develop a more tailored deodorization process for this type of packaging. Then maybe a last thing that we have noticed is that if we increase the temperature, there is an increase in deodorization efficiency, but it's not a huge difference. So if we increase around 40 degrees, we see that the deodorization efficiency increase around 10% also. So this was the main results that I wanted to show you today. So thank you for your attention, and also thank you, Ilse and Philip, for organizing and moderating this session.